Hello, everyone. Thank you for tuning in. I was asked to talk about the subject Hadean geodynamics. I jumped at the opportunity to do so in part because I find the subject interesting, and in part because I thought it'd be easy to put together a talk on this subject because this slide shows essentially everything we know about Hadean geodynamics. Don't worry, there's nothing wrong with your screen. This is an intentionally blank page. The problem here is that we have an extremely limited number of samples that date to this era of Earth history. This is unfortunate because it's pretty clear that this time shortly after Earth formation established many of the first order features of our planet. So what I'd like to do today is use what little information we do have from terrestrial materials that date to the Hadean, along with information we have been able to obtain from nearby planetary neighbors, particularly the Moon, along with an improved theoretical understanding of what should happen in a planet's interior shortly following its formation, to provide a glimpse for you of what the Hadean Earth may have been doing. The story will start at the time of the giant impact. The reasons for doing this, if you saw Miki Nakajima's talk, you saw that impacts of this scale are so violent that they basically represent resetting events for the impacted planet. We can investigate when this impact occurred in the Earth-Moon system by comparing ages for the two bodies, and that's done on the diagram on the right here. If you look first at the Moon column provides age estimates for both the lunar crust and model ages for the lunar interior. And while these scatter quite a bit, they do tend to cluster in the age range 4.35 to 4.45 billion years. This is surprising in a solar system that's 4.568 billion years old, and it implies that the moon-forming impact may have occurred quite late in the planet formation timescale. So if this model of moon formation is correct, we would expect to see similar ages for the Earth, or at least for those portions of it that were reset by the impact. The column for Earth's early crust in this diagram, for example, shows the oldest material in our collection to be 4.37 billion-year-old zircons from Jack Hills in Western Australia. There are also rock formations now known that are at least 4.03 billion years old and perhaps as old as 4.28 billion years old, as I'll discuss in more detail later. Model ages for the Earth's interior range more widely, for reasons I'll also discuss later, but at least some of them are also consistent with this circa 4.4 billion-year-old age for moon formation. Some aspects of Earth, however, appear to predate this age. Both the rubidium-strontium and the manganese-chromium systems have been used to show that Earth was volatile depleted within no more than 3 million years of solar system formation, most likely because the materials that form the Earth were also volatile depleted. This means the moon-forming impact may have increased the volatile depletion of Earth, but the Earth was depleted in volatile elements even before the impact. The other feature of Earth that dates to earliest Earth history is its core. We now have clear indications from the decay of 182 hafnium to 182 tungsten that a single-stage formation age of Earth's core is around 30 million years after solar system formation, or about 4.54 billion years ago. As Earth's core likely continued to grow throughout the early history of planet formation, this is most likely just an approximate age, but it does indicate that core formation likely predates the moon-forming event. One thing that's clear is that the impacts of this magnitude cause lots of melting of the impacted objects, most likely even the formation of global oceans of magma. The idea of a magma ocean was first developed as a result of the lunar missions, as the Moon shows the effect of such an event clearly, while the Earth does not. The differentiation of an ocean of magma as it crystallizes can create extreme compositional differences between the interior and the crust, and that's shown here for the lunar magma ocean. The idea is that a partially or maybe even totally molten moon underwent fractional crystallization as it cooled. The dense iron metal, of which there's not a lot in the moon because most of the impactor's core probably joined the Earth's core, sank to the middle to form the small core of the moon. The silicate liquid then began crystallization with magnesium-rich phases like olivine and pyroxene, and because these phases are denser than the magma, they would have sunk and accumulated to form the solid mantle of the moon. And this material eventually was going to serve as the source regions for Mare basalt eruptions that occurred between 3 and 4 billion years ago. So removal of these phases causes the calcium and aluminum abundance in the remaining magma to increase, eventually to the point where it saturates in anorthite feldspar. This feldspar, however, when it crystallizes, is less dense than the magma, so it floats to the surface and forms the north-acidic highlands of the moon in much the same way that icebergs float on top of the ocean. The diagram on the right shows the chemical consequences of this evolution for a series of elements known as incompatible lithophile elements. Lithophile means that they prefer silicates, and incompatible means that they don't fit well into the crystal structure of olivine and pyroxene. As a result, when olivine and pyroxene crystallize from the magma, they don't incorporate these elements. This leaves the lunar mantle with very low concentrations of this particular group of elements. The same is true for feldspar, with one exception, and that's europium. Europium is the one rare earth element that under most planetary conditions can be present as both the +2 and the +3 oxidation state. In the +2 oxidation state, it can substitute for calcium in the feldspar structure, and it's relatively enriched in abundance compared to the other rare earths in feldspar. So the crystallization of these phases that don't incorporate much of these elements leaves the remaining magma very enriched. So a good representative of this late-stage magma is creep. Creep gets its name from its enrichment in potassium, rare earth elements, and phosphorus, and it's a rather peculiar magma type known only on the moon. If you look at this pattern for creep, the dip in the pattern at europium is a sign that creep formed after the feldspar had been removed from the magma. The feldspar had taken a good amount of europium with it. The big dip in potassium, however, is not due to magma ocean evolution, but it's instead a sign of the volatile depletion of the moon, as potassium is the only element in this list that is moderately volatile. And the patterns here are created by normalizing to a type of meteorite that has near solar abundances in all but the most volatile elements. Another important observation here is that among these elements are uranium, thorium, and potassium, the three long-lived radioactive isotopes that are the primary heat sources for planetary interiors. At least the deep interior of the moon thus is severely depleted in these elements, and this likely limited the amount of convection and hence dynamics of the lunar interior after the crystallization of the magma ocean. These radioactive elements, however, also provide the clocks by which we can date this differentiation event. And as you can see here, all three of these major compositional components of the moon provide ages between 4.35 and 4.4 billion years. And this is consistent with the idea that these three major components of the moon were formed in a single event. And this is what is predicted by the magma ocean model. So we see something vaguely similar to these compositional distinct materials on the moon on the Earth. The diagram on the left here shows the incompatible element abundances for continental crust that on average is strongly enriched in the highly incompatible elements, and this is reminiscent of lunar creep. Complementary to this enriched pattern is the depleted incompatible element abundances of the mantle that supplies the basaltic volcanism at ocean ridges. This has given rise to box models for the solid Earth, shown on the right here, that have a very small mass fraction of continental crust that is highly enriched in incompatible elements, with a complementary volume of depleted mantle that can range from something like 30 to 90% of the mantle, depending on what elements you base your mass balance on. And then completing the mass balance is some portion of the undifferentiated mantle that again can range somewhere between a small fraction to more than half of the mantle. So this story at first appears similar to that of the lunar magma ocean story for the moon, but if you investigate when this chemical separation occurred, you get a wide range of results, none of which date back to the Hadean. Instead, most estimates of when this chemical separation occurred are close to about half the age of the Earth. Now, most likely these ages don't represent any single discrete crust formation event, but they're instead something like an average age for crust mantle differentiation that has been occurring throughout Earth history. In other words, these components of Earth are not the result of an initial terrestrial magma ocean. As with the moon, this differentiation process has moved a large fraction of Earth's radioactive elements towards the surface. Something like 30 to 35% of all of Earth's uranium, thorium, and potassium are in the continental crust. So one would think that this would have important consequences for the dynamics of Earth's interior, and it likely has, but not in the obvious way of reducing that activity. To understand the consequences of the concentration of these elements in the crust for the interior dynamics of the planet requires us to understand the rate at which continental crust formed. And on this point, the opinions vary very widely. This diagram is perhaps the most embarrassing one in our field. It shows a number of estimates for the volume of continental crust on Earth throughout Earth history, with 100% being the present volume of the continental crust. What's embarrassing about this plot is that estimates include about every possibility there is, from lots of crust early in Earth history to none. And even some models suggest that the present volume of the continents is less than it was at times in the past. Now there's a clear explanation why we have such poor constraints on the volume of continents through time. And that's because Earth is an active planet. The right-hand animation here shows a computer model of the dynamics of Earth's interior that was provided by my colleague Peter Van Kaken. What this shows is a thin layer of oceanic crust, that red band on the outer circumference, sinks back into the mantle and then gets mixed back into the mantle by the stirring that's driven by mantle convection. The net result of this process is that most of the Earth's surface is covered by very young crust, as shown on the left. So the ocean basins have no crust older than about 200 to 300 million years old. So thinking about the last slide, estimating how much continental crust was present in the past is confounded by the fact that we have almost no idea of how much of it has been subducted into Earth's interior and lost from the surface record. But this is a topic where we're making some headway, at least in regards to the earliest Earth. This has come about through the application of what are known as short-lived radionuclides. These are radioactive isotopes with half-lives long enough to survive the transport times from the stars that made them, and all heavy elements are made in stars, and the incorporation of these elements in the planets when the solar system was forming. In this case, 146 samarium decays to 142 neodymium with a half-life of a bit over 100 million years. What this means is that the changes in the ratio of 142 neodymium to a stable isotope of neodymium, such as 144 in this diagram, reflect changes in the ratio of samarium to neodymium that are caused by chemical differentiation events, but only while 146 samarium was still alive. Given our current measurement precisions, that means this system is recording Earth differentiation events for about the first 500 million years of Earth history. After about 4 billion years ago, one can no longer create variability in 144 neodymium. One can only reduce the variability by mixing materials with high ratios with other materials that have low ratios of this element. The left-hand figure here shows a wide range in 142, 144 neodymium in early Earth history that's much reduced by 2.5 billion years. And though there is a large gap in the data throughout much of the middle of Earth history, there are a lot of data in modern rocks that show values mostly within measurement precision of one another. A possible explanation for this is shown in the pair of figures on the right from a recent paper by Rosas and Cornaga. The top figure here shows essentially the same thing as on the left figure, but the blue fields show the changes that would be expected in the isotopic composition that occur as the result of recycling of ancient crust into the interior and then mixing that crust with its incompatible element depleted complement and erasing the isotopic variation in the process. The bottom figure shows the evolving rate of crustal recycling needed to explain the isotope data in this model. And this model requires a very high rate of crustal recycling prior to 4 billion years. This rate of recycling declines gradually, but it still remains substantial throughout Earth history. This is the type of the model that predicts that the volume of continental crust really hasn't changed that much throughout Earth history because one is producing as much crust as one is recycling through time. So what are the options when we consider planetary dynamics? There is the kind of plate tectonics we know today, where new oceanic crust is made along ocean ridges. It survives at Earth's surface for 100 to 200 million years, and then it sinks back into the mantle through the process of subduction. As it subducts, it makes some continental crust along the way through the volcanism that occurs along convergent plate boundaries as the sinking plate releases the water it carries down from the surface into the overlying mantle. So this type of geodynamics results in rather efficient stirring of Earth's interior along the lines that I showed you in the animation from Peter Van Kaken. What we don't understand very well is how this form of plate tectonics may have changed back in time as the temperature and possibly also the volatile contents of Earth's interior evolved. There are interesting models, for example those pursued by Van Hunen and others, that suggest that the hotter Hadean and Archean mantle would support a more episodic subduction. In some cases, the subduction would look more like drips or big Rayleigh-Taylor instabilities as the crust just founders and sinks almost vertically into the mantle, much like the way it does in the animation that I showed. The consequences of this type of magmatism for the volcanism that occurs on convergent margins and the types of crust created in those processes are not all that clear because of the change in dip from the near vertical subduction to the more sort of 45-degree dip angles that typify modern convergent margins. Another style of plate tectonics is what Brad Foley describes as mobile lid tectonics. that's similar in some ways to modern subduction, but runs at slower and quite variable rates. And I'll refer you to his talk for the details on this process. Finally, there's the other end member, stagnant lid tectonics. This is where the planet has a thick crust or a lithosphere that's pretty much just sits there while convection is occurring in the mantle below it. This is the type of tectonics that is rumored to be characteristic of Venus, for example. Stagnant lids, however, limit the amount of heat that can get out of the planetary interior because that heat has to conduct through the thick lithosphere, and conduction through rock is terribly inefficient. This gives rise to what are known as heat pipe models, where the interior gets hot enough that it drives its way through the lithosphere, resulting in extreme high volume volcanic resurfacing of the surface of the planet. Again, something like this has been suggested to occur on Venus. This type of tectonics, however, effectively separates the crust from the interior, and hence it limits the amount of crustal recycling that can occur, which likely is a problem given the evidence for early crust recycling that I went through on the last slide. We know that plate tectonics is occurring on Earth today, but there's considerable disagreement on when plate tectonics started. One school points out that the obvious structural features associated with subduction, things like ophiolites, high pressure, low temperature metamorphic rocks like blue schists and the minerals they carry like jadeite and ruby, these are found only in fairly recent geologic record, most likely within the last billion years or so. If you want a very nice presentation of this idea, I recommend the talk given by Bob Stern a couple of years ago that's available on the YouTube through the link that's shown on this slide. The counters to this argument for a late initiation into plate subduction include that such features may not be characteristic of subduction on the hotter early Earth. And then there's also the question of whether these features would be preserved in old rocks. A good example is that most early Archean terrains have been to amphibolite or higher metamorphic conditions sometime during their lifetimes. So if they were originally blue schist facies, these rocks would have been converted to higher temperature metamorphic rocks by these later metamorphic events. A compelling argument for plate subduction that occurred much earlier in Earth history comes from an unexpected place, the minerals that are trapped in diamond. Diamonds often contain a variety of minerals that were present when the diamond was forming. Diamond is such a well put together mineral that once it traps these inclusions, it effectively protects them from their surroundings. So even though you can analyze these inclusions at the room temperature and pressure of the laboratory, the conditions that the minerals record are those of their formation deep in the mantle, in some cases as deep as the uppermost lower mantle. Two types of inclusion minerals dominate in diamonds, ones that likely are derived from the high pressure form of basalt known as eclogite, and the other from the rock type typical of the mantle, is peridotite. The age of these inclusion minerals can be determined using the rhenium-osmium isotope system. So what Shari and Richardson pointed out in this paper is that eclogitic inclusions can be found that are as old as 3 billion years, but no older, whereas the peridotitic inclusions can be older, as much as 3.5 billion years in age. They suggest that the onset of eclogitic inclusions at 3 billion years represented the initiation of plate subduction at that time. Now, given that some of these eclogitic inclusions have oxygen and sulfur isotopic compositions that are consistent with them having been at Earth's surface at one time, their appearance as diamond inclusions is strong evidence that at least some basaltic crustal materials were being subducted to at least a couple of 100 kilometers depth in the mantle by 3 billion years ago. An increasing number of studies are pointing to an apparent change in the nature of continental crust production at around 3 to 3.5 billion years ago. These changes are often interpreted as signaling the onset of plate subduction on Earth, although that's not necessarily the only interpretation. On the right, this figure is from the paper of Cawin and others, and this is a global comparison of detrital zircons that's based on their hafnium isotopic composition. There's a bit of interpretation of these data, but the green bars show the number of samples that they conclude are of likely mantle origin, meaning new crust created from melting in the mantle, while the gray bars show those crustal samples that likely include a substantial contribution from pre-existing crust, either by contamination of mantle-derived melts or in fact from remelting that pre-existing crust. The curve through the red dots then shows the proportion of mantle-derived crust as opposed to reworked older crust through time. And these data led the authors to two important conclusions for our subject today. First is that there was a lot more continental crust present in the Archean than is preserved today, so a lot of Archean crust has been recycled. And secondly, that there was a shift to extensive crustal recycling beginning at about 3 billion years ago that the authors suggest reflects the onset of subduction. You can see the same concept in more detail in the plot on the left that shows the hafnium isotopic composition of zircons from igneous rocks from the Acasta region of the Slave Craton in the Northwest Territories of Canada. Acasta is the site of the oldest rock that's dated by zircon at 4.02 billion years. On this type of diagram, values of epsilon hafnium that are near zero are consistent with a primary mantle origin, whereas negative values are more characteristic of derivation from older crustal rocks. So what this data set suggests is that the oldest crust in the Acasta region was extracted from the mantle at about 4.2 billion years ago. And in fact, there is one xenocrystic zircon in one Acasta sample that has a core of 4.2 billion years in age. But after this initial crust formation event, the younger rocks primarily were made by remelting of that older crust until about 3.6 billion years. At 3.6 billion years, the hafnium isotopic compositions you can see return towards zero, and this suggests another episode of new crust generation from the mantle. So you can actually see similar steps in zircon hafnium isotopic evolution in several old terrains, though the steps don't always occur at the same age. The interpretation of these steps are not entirely clear. They're often interpreted as signaling the onset of subduction in these regions, but nevertheless, they clearly show that there was a significant change in the nature of crust formation occurring about 3 to 3.5 billion years ago. So finally, my preference in terms of interpreting whether a rock formed in a subduction zone or not is the use of compositional characteristics in old rocks that in modern rocks are considered typical of convergent margin volcanism. Shown here is a data set that was produced by Jonathan O'Neill for a group of very old metabasaltic rocks from the shores of Hudson's Bay in Canada. This is a terrain known as the Nouveau-Agatic supercrustal belt. This relatively small area shows 3 compositional types that have distinct rare earth element patterns. And although there's not a resolvable age difference between these 3 units, the stratigraphic interpretation of their relative ages suggests that the first sequence in this province is characterized by flat rare earth element patterns in the high titanium group that's shown here. And these kind of patterns are expected for melting of primitive mantle. This group of rocks also follows differentiation trends that are consistent with shallow differentiation of a relatively dry magma. The next sequence erupted in this area has a quite unusual rare earth element pattern that's characterized by depletion in the middle rare earth elements and then enrichment in the lightest rare earth elements. This type of pattern is found today predominantly in a rock type known as bonanite, which is found essentially only in convergent margin settings. The interpretation of this pattern is that the source rock for these volcanic rocks had experienced a melt removal event at some time in the past that had extracted the more incompatible light rare earth elements from that source. But then this source was later affected by a metasomatic event that added back the light rare earth elements, most likely from the addition of some melt component. So for bonanites, this metasomatism reflects the input of hydrous melts from the subducting plate into the overlying mantle wedge that was composed predominantly of previously depleted peridotite. The fauna unit, this enriched low titanium unit, then has flat heavy rare earth element patterns with significant enrichment in the light rare earth elements, as is typical of many convergent margin magmas, and for that matter, many other magma types as well. Both the depleted low titanium and the enriched low titanium groups follow differentiation trends that are consistent with low pressure differentiation of relatively wet magmas, as you would be expected for convergent margin magmas. So the cartoons on the right show a hypothesized tectonic setting for the Nouveau-Agatic, where the first sequence, the high titanium rocks, represent the melting of dry mantle in the shallow parts of the Earth, forming a basaltic platform, if you will, think of something like Iceland. This serves as essentially the core against which subduction begins along its margins. The subduction brings surface waters down into the areas below this platform, and those instigate melting, both of the slab and the overlying mantle, that gives rise to the bonanites. And then as this subduction continues, the depleted mantle that was the source of the bonanites is sort of swept away in normal convergent margin magma flow, and it's replaced by fertile mantle that then receives the metasomatism from the downgoing plate and instigates convergent margin volcanism. So this sequence of events is basically identical to what one sees in modern oceanic subduction zones, for example, the Marianas Arc in the Western Pacific. Okay, Okay, I'll throw in one more not very definitive plug for an early start to plate tectonics, and this comes from an unlikely place, the presence of a magnetic field on the early Earth. So Earth's geodynamo is driven primarily by heat loss from the core to the overlying mantle, and the rate of that heat loss is highest when the temperature difference between the core mantle boundary is very large. So one very effective way to cool the mantle that's just above the core is through the subduction of crust to the core mantle boundary. Rock magnetism is not my field, but my understanding is that there's little disagreement about the presence of a terrestrial magnetic field that was similar strength to the present day field, extending back to about 3 billion years ago. Before that, there are reports from a very detailed study of the Hadean zircons from Australia that suggest that the field strength extends back to earlier than 4 billion years. Now, this point is under discussion because of the possibility that the magnetic field measurements of these samples possibly are due to magnetic inclusions in the zircons that formed by alteration or metamorphism long after the zircons themselves formed. I don't understand the details of the arguments well enough to wade into the fray here, but I do recommend this comment and reply in EPSL that will give you a good picture of both sides of the discussion. Okay, coming close to the end now. I want to cover what information we have about the Earth's surface environment in the Hadean. And this, in fact, is one of the bigger surprises that's come out of recent work. What is clear from the oldest terrestrial rocks and minerals that we have available for study is that there was liquid water present on Earth's surface, certainly at 3.8 billion years ago, but likely as long ago as 4.3 billion years. And this slide shows the data that supports this conclusion. On the top left are structures that suggest the basalts in the Nuvuagittuk area were erupted into liquid water. This is what pillow basalts look like after being subjected to the type of metamorphism the Nuvuagittuk rocks have experienced. The bottom left shows the chemical data for these same rocks that documents the almost complete removal of calcium from them. And this removal of calcium is a chemical signal that's typical of severe alteration caused by circulating hot water. Think, for example, of hydrothermal circulation in seafloor basalts. The middle diagram shows oxygen isotope data for the Hadean zircons from Western Australia. And these values document oxygen isotopic compositions that are well into the range typical of granites that are formed by melting of water-rich rocks in the shallow crust. This inference is supported in the recent Turner et al. Paper that's quoted here by trace element data for these zircons that they interpret as reflecting the origin of the zircon in a rock of andesitic composition. And this source rock has trace element characteristics similar to the andesites that are produced in convergent margins in the modern world. So this idea is consistent with the cold geotherm that's inferred for the rocks that crystallize these zircons, as is deduced from the study of the composition of the minerals that are included in the zircon, in particular this paper by Hopkins et al. The inferred melting temperatures and pressures that these authors get for the parental rocks to these zircons are shown in the shaded region in this pressure temperature diagram. And though it covers a fair amount of space, particularly in the pressure axis, the data are consistent with a relatively high pressure, low temperature melting regime that would be consistent with the cold types of geotherms seen in modern convergent margins. So these kind of results for the oldest terrestrial materials that we have available for study suggest that the recovery of the planet from the hellish conditions that gave the Hadean era its name was pretty quick, so that by 4.3 billion years ago, Earth's surface was cool enough to support the existence of liquid water. And given that the oldest preserved fossils are on the order of 3.5 to 3.9 billion years in age, depending on who you ask, whether they're in fact fossil life, if you had a clement surface on the Earth by 4.3 billion years ago, this gives you an extra 600 to 800 million years of clement surface for organic chemistry to do its thing and to develop the life forms that are only beginning to be preserved by, let's say, 3.5 billion years ago. Okay, so we've reached the conclusions, and I'll just summarize them here. As I mentioned, the moon-forming impact likely represents, in essence, the start of the modern Earth. There was an Earth there before that, but in terms of our interpretation of what the Earth looks like today, the starting time really was following this giant impact. There is evidence now that the early Earth's interior was in fact compositionally heterogeneous and is probably caused by igneous differentiation, perhaps related to a magma ocean induced by the giant impact, perhaps indicative of early crust forming events, but it was present. An interesting aspect of, though, is that the Earth's current continental crust and mantle compositional differences are not due to these early events, They instead represent the formation of continental crust pretty much over Earth history. We don't really know what geodynamics was like in the Hadean. We have some speculation. The point that I would try to stress here is that we have pretty good evidence for the initial erasing of early formed chemical heterogeneities in the Earth. And the most likely explanation for this, at least in my opinion, is that there was substantial crustal recycling in the early Earth and the mixing of that into the mantle. And the easiest way, of course, to do that is through plate tectonics and subduction of the type that we know today, or perhaps slightly modified given the different thermal conditions existing in the Hadean mantle. And then finally, I think the biggest surprise to come from this work is that Earth's surface environment by maybe even 4.4 billion years ago was marked by the presence of liquid water, which sets a certain temperature range for the Earth's surface. What this suggests is the Earth returned to more or less clement conditions very quickly after the moon forming impact. Particularly if the moon forming impact occurred as late as 4.4 billion years, it probably only took as little as tens of millions of years before the surface of Earth became a place where life had a chance to develop. Okay, that's the story. So I'd like to thank you for your attention and hope you enjoy the presentation. Thanks much.